Merhabalar, sesimi alabiliyor musunuz?
Evet.
Merhabalar, evet alıyoruz.
Merhabalar, tamamdır. Değerli katılımcılar, 9. Uluslararası Öğrenciler Bilim Kongresi kapsamında gerçekleştirdiğimiz 23 Mayıs 2025 tarihli 27 numaralı oturumu açıyorum. Hepiniz hoş geldiniz. Ben Gıda Mühendisi Doktor Bilge Taşkın. Bu oturumu ben yöneteceğim. Oturumda toplam 6 tane sunumumuz olacak ve bu sunumlar her bir sunum için öncelikle 15 dakika zaman ayrıldı ve bu süre içerisine soru ve cevap kısmı da dahil. Katılımcıların bu sebeple bu süreye dikkat etmesini önemli rica ediyoruz. Sunumlara bu programda belirlenen sıra ile devam edeceğiz. Sunum başlarında ekran görüntüsü alınması için biraz beklenebilir. Bu ilk sunumun ilk sunulacağı kapak sayfası için diyebilirim. En son oturumun sonunda da topluca bir ekran görüntüsü alınacağı, sizin katılımınızın kanıtı olarak ekran görüntüsü alınacağı için de herkesin sunum boyunca burada kalmasını diliyoruz ve kameraların da açık olmasını istiyoruz. Sunum sonunda sizden bunu rica edeceğiz. En son olarak yazar isimleri ve bildiri başlığını içeren sertifikalar şeyden sonra bu kongreden sonra size dijital olarak gönderilecek. Dear participants, welcome to session 27th of the 9th International Student Science Congress, which is being held on today, which is 23rd May of 2025. I am food engineer Bilge Taşkın, and I'll be chairing this session for you. There will be a total of 6 presentations, and each presentation, including the questions and answers, will last 15 minutes. So please keep your questions and answers within this time, and we will follow the predetermined order of the presentations which are given in the program. And please wait a few seconds at the start of each presentation for a screenshot to be taken. At the end of the session, a group screenshot will be taken, so please stay and keep your cameras on. Certificates, including names and presentation titles, will be sent digitally after the Congress. So thank you for your cooperation. If you have any questions, I can answer now. Herhangi bir sorunuz yoksa ilk sunumla başlayabiliriz arkadaşlar. İlk sunumumuz Eyyup Yalçın ve Merve Karaman'ın oksalik asit ile bazı geçiş metal komplekslerinin sentezi, karakterizasyonu ve biyolojik uygulamaları. Evet, sanıyorum Merve Hanım siz sunuyorsunuz.
Evet, evet doğrudur hocam. Başlayabilir miyim?
Başlayabilirsiniz. Görüntünüzü
Hocam kameram sanırım çalışmıyor. Öyle bir sorunumuz var. Yani
ekran görüntüsünü paylaşabilirsiniz. Sizin sunumunuzun ilk
bir saniye. Paylaşıyorum gibi görünüyor ama paylaşmıyor mu şu an?
diğer arkadaşlarım görebiliyorlar mı? Ben göremiyorum.
Hayır hocam, gelmedi.
Şöyle tüm ekran desem bunu paylaşacak mı? Şu an sanırım tüm ekranı paylaşıyor. Doğru mudur hocam? Görebiliyor musunuz?
Şu anda görebiliyoruz. Tamam.
Tamam. Bu şekilde yapalım o zaman.
Tamam.
Bekleyeyim mi bu ekran görüntüsü almanız için?
Sanıyorum almışlardır diye tahmin ediyorum. Biz başlayabiliriz sürenizi yememek adına.
Tamam. Çalışmamız oksalik asit ve bazı geçiş metal komplekslerinin sentezi, karakterizasyonu ve biyolojik uygulamaları üzerine. Bu kapsamda öncelikle oksalik asit ve metal komplekslerinin genel özelliklerinden, daha sonra geçiş metallerinin biyolojik öneminden bahsedeceğim. Potansiyel biyolojik aktiviteleri, çalışmanın amacı, deneysel yöntem, sonuçlar ve kaynakları sunacağım. Oksalik asit ve metal komplekslerinin genel özelliklerini incelediğimizde oksalik asitin yapısı şekil 1'de verildiği gibi 2 karboksilik asit grubu içeren doğada birçok bitkide bulunan güçlü bir dikarboksilik asit yapısında 2 karboksilik aside sahip olduğundan dolayı buradaki oksijen uçlarından metallere koordine olabilme özelliğine sahip iki dişli ligand olarak davranıyor. Temizleyici ve artıcı ajan metal iyonlarının komplekslenmesinde ve organik sentezlerde de ara madde olarak yaygın olarak kullanılıyor. İlaç geliştirme ve antimikrobiyal uygulamalarına baktığımızda özellikle antibakteriyel, antifungal, antiviral etkileri gösterdiği biliniyor. Bu metal iyonlarının biyolojik aktivitesi de bu komplekslerin modifiye edilmesiyle değiştirilebiliyor. Örneğin bakır oksalik asit kompleksleri bakteriyel hücre duvarına zarar verebiliyor ve patojenleri inhibe edebiliyor. Bu özelliği sayesinde de kullanılıyor. Antioksidan ve anti kanser uygulamaları da mevcut. Özellikle kobalt ve bakır içeren kompleksleri reaktif oksijen türlerinin oluşumunu engelleyerek bu etkiyi gösteriyor. Aynı zamanda oksalik asit komplekslerinin DNA'ya bağlanma özellikleri sayesinde de antikanser ilaç araştırmaları arasında da ilgi çekiyor. Kompleksin yapısına bağlı olarak hücre içi mekanizmalarda apoptozu indükleyebiliyor. Biyosensör ve görüntüleme ajanı olarak da kullanılabiliyor. Metal kompleksleri biyolojik ortamda spesifik metal iyonlarını tanıyabilen sensörlerin geliştirilmesinde kullanılıyor. Bazı metal oksalik asit kompleksleri MRI kontrast maddesi veya optik görüntüleme ajanı olarak çalışabiliyor. Bu çalışmanın amacı oksalik asit ile demir 2, kobalt 2 ve bakır 2 geçiş metalleri arasında kompleks bileşikler sentezlemek. Bu komplekslerin yapısal ve termal özelliklerini FTIR, XRD ve TGA gibi analiz yöntemlerle karakterize etmekti. Ayrıca bu komplekslerin potansiyel biyolojik ve sağlıkla ilişkili uygulamaların araştırılması hedeflenmişti. Deneysel kısımda oksalik asit ve metal tuz oranı 1'e 2 olacak şekilde çalışıldı. Oksalik asitte 2 bağlanma ucu olduğundan dolayı bu oran tercih edildi. Metal tuzu olarak kobalt 2 klorür hegzahidrat, demir 2 klorür trihidrat ve bakır 2 nitrat trihidrat başlangıç tuzları kullanıldı. Çözgen ortamı etanol su 5'e 1 olacak şekilde tercih edildi. 60 santigrat derecede 1 saat karıştırıldı ve karıştırma sonunda oluşan metal oksalat kompleksleri çöktü. Daha sonra süzme işlemi yapıldı. Süzme sonrası 55 santigrat derecede 4 saat etüvde bekletilerek ürünler kurutuldu. Görmüş olduğunuz görsel elde ettiğimiz ürünlere ait. Pembe renkli olan kobalt oksalat kompleksi, sarı renkli olan demir oksalat kompleksi ve mavi renkli olan bakır oksalat kompleksi. Daha sonra elde edilen komplekslere FTIR spektrumuyla karakterizasyonu gerçekleştirildi. FTIR spektrumunda özellikle 600 ila 400 santim üzeri eksi 1 aralığında metal oksit bağlarının varlığı bize oksalik asitle metallerin koordine olduğunu gösterdi. Aynı zamanda elde edilen ürünlerin renkli olması tabii ki metallerin sayesinde olduğu için ve ürünlere ait spektrum piklerinde 300, 3400, 3300 civarında piklerin varlığı yine OH gerilme titreşimlerine, suya ait oluşan yapılardaki kristal suyuna ait gerilme titreşimlerine ait olduğu tespit edildi. Aynı zamanda 1600, 1400, 1300, 1000 arasındaki santim üzeri eksi 1 arasındaki piklerde karbon oksijen, karbon tekli bağları ve karbon oksijen çifte bağlarına ilişkin olduğu bilinmekte. Dolayısıyla FTIR spektrumuyla yapıların sentezlendiği tespit edildi. Aynı zamanda bu komplekslere termal kararlılık incelemesi yapıldı. Bu kapsamda nitrojen atmosferinde 100 mililitre bölü dakika olacak şekilde çalışma yapıldı. 10 derece bölü dakika ısıtma hızında gerçekleştirilen analiz sonucunda elde ettiğimiz eğriler bu şekilde. Kütle kaybına karşı sıcaklık eğrileri. Kobalt kompleksine baktığımız zaman 50 ila 130 santigrat derecede %4'lük bir kütle kaybına karşılık gelen kristal koordinasyon suyu kaybı gözlenmekte. 180-360 derece arasında en yüksek kütle kaybı görülmekte ki bu da oksalik asitten kaynaklı bir kütle kaybı. Yani ligandın parçalanmasına ilişkin, organik kısmın parçalanmasına ilişkin bir kütle kaybı. 360-700 santigrat derece arasında en son karbon kalıntılarının uzaklaşması mevcut. Nihai olarak bütün türler için oksitli türevler, yani metal oksit türevlerinin kalıntı olarak kaldığı düşünülüyor. Yine bakır kompleksi için, bakır oksalat kompleksi için 50 ila 130 santigrat derece arasında %3'lük bir yüzey adsorblanmış su kaybı olduğu görülmekte. 180-300 santigrat derece arasında %45'lik ligand ayrışması, 300-800 santigrat derece arasında %14 kütle kaybına karşılık gelen yine karbonlu türlerin ayrışmasıyla nihai olarak yine bakır oksit kalıntısının kaldığı düşünülmekte. Demir 2 oksalat kompleksi için yine 60 ve 140 santigrat derece arasında %3'lük su kaybı görülmekte. 190-330 santigrat derece arasında %43'lük kütle kaybı organik yapının ayrışması ile ilişkilendiriliyor. 330-750 santigrat derece arasındaki %17'lik kayıp da yine karbonlu türlerin uzaklaşması şeklinde yorumlanabilir. Bu eğrileri incelediğimiz zaman en yüksek termal kararlılığın kobalt 2 oksalat kompleksinde olduğu, daha sonra demirin en düşük kararlılığında yine bakıra ait olduğu gözlendi. Yine de her halükarda bütün kompleksler için termal kararlılığın iyi olduğu söylenebilir. Yaklaşık 180 dereceye kadar hepsinin bozulmadan kaldığını söyleyebiliriz. Oksalik asit, demir, bakır ve kobalt kompleksleri için XRD karakterizasyonunu da gerçekleştirdik. Bu kapsamda kobalt 2 oksalat kompleksi için elde edilen pikler literatürdeki beta fazına karşılık gelen beta oksalat dihidrat yapısıyla uyum göstermiştir.
Son 3 dakikamız.
Karakteristik pikler 2 teta 18.7 ve 34.9 olarak rapor edilmiştir. Bakır 2 oksalat kompleksi için elde edilen pikler literatürdeki bakır oksalat N hidrat yapısıyla uyum içerisindedir. Belirgin pikler 2 teta 22.9, özellikle en şiddetli pikimiz 36.2, 36.9, 46.8 ve 52.1 olarak rapor edilmiştir ki spektrumumuzda bu pikler mevcuttur. Son olarak demir 2 oksalat kompleksi için elde edilen pikler literatürdeki alfa demir oksalat dihidrat yapısıyla uyum göstermiştir. Belirgin pikler 18.6, 24.7, 30, 33, 40.2, 45, 48.3 ve 50.4 olarak gözlenmiştir. Özellikle bakır ve demir 2 oksalat komplekslerinin daha kristalinik yapıda olduğunu söyleyebiliriz. İlerleyemiyorum şu anda ama. Duyabiliyor musunuz?
Biz duyuyoruz. Evet, ilerledi sanırım.
Tamam. Sonuç olarak oksalik asit ile demir 2, kobalt 2 ve bakır 2 geçiş metal komplekslerinin sentezi başarıyla gerçekleştirilmiştir. FTIR analizleri ligandın karboksilat grubundan metal iyonlarına koordinasyon yaptığını göstermiştir. TGA verileri komplekslerin çok basamaklı termal bozulma özelliği sergilediğini ve kobalt 2 kompleksinin en yüksek termal kararlılığa sahip olduğunu ortaya koymuştur ve XRD analizleri komplekslerin kristalin yapıya sahip olduğunu, literatürdeki benzer komplekslerle uyumlu paternler verdiğini göstermiştir. Bu karakterizasyon bulguları komplekslerin yapısal doğrulamasını sağlamış ve ileride planlanan biyolojik testler için sağlam bir temel oluşturmuştur. Benim sunumum bu kadar.
Teşekkür ederiz.
Ben teşekkür ederim.
Soru cevap için 1 dakikamız var. Sorusu olan var ise alabiliriz. Yok ise sonraki sunuma geçebiliriz. Sanıyorum yok. Merve Hanım teşekkürler.
Ben teşekkür ederim, sağ olun.
Sonraki sunumumuz Hande Savran.
Merhabalar, ekranımı görebiliyor musunuz?
Merhaba, görüyoruz Hande Hanım. Hande Savran, Tayfur, Yavuzbarut, Kemal, Bartu, Aydın'ın çalışması. Enhancing Productivity Through the Design of a Special Die for M30-138 DIN 931 Production.
Evet. M30
Peki,
diyebiliriz sadece.
evet, başlayabiliriz Hande Hanım.
Tamamdır, teşekkürler.
Teşekkür ederim.
Hello everyone, I am Hande Savran and I work as an R&D engineer at Norm Tooling. Concurrently, I am pursuing my master's degree in Department of Mechanical Engineering at İzmir Katip University. Today, I will be presenting our study named Enhancing Productivity Through the Design of a Special Die for M30 Production, which is one of the research and development works at Norm Tooling R&D Center. This study was conducted in collaboration with Tayfur Yavuzbarut and Kemal Bartu Aydın. In this presentation, we will detail the innovative solution we developed to address a significant productivity challenge and concurrent in fastener production. The outline of our presentation is as follows. We will begin with introduction to cold forming and the manufacturing of cold forming dies. Subsequently, I will present our current situation analysis, the fundamental reasons our improvement to design and simulation processes, and finally, the optimum design and the outcomes we achieve. Our objective is to convey how this work adds value to industrial processes. My presentation will last approximately 10 minutes, after which I will be happy to answer any questions you may have. What is cold forming? Cold forming is a manufacturing process that shapes materials at room temperature without heating using dies and presses. This method offers several advantages, including high precision, excellent service quality, and increased material strength. As you can see in the slide, the workpiece is progressively shaped to successive stations to obtain the final product. Each stage allows for the gradual deformation of the material, which directly impacts the quality and mechanical properties of the final product. Now we understand what cold forming is. In this slide, we will examine the stage of the manufacturing processes for dies used in cold forming. Each stage is crucial for the quality and performance of the final die. The first stage is preparation of die materials. Tungsten carbide and steel materials are cut into appropriate sizes. The second stage is rough machining. Cold forming die parts made from tool steel are subjected to rough machining on CNC lathes before heat treatment to achieve the desired hardness values. Similarly, tungsten carbide parts are also brought to appropriate dimensions. The third stage is electrical discharge machining. After steel and tungsten carbide are combined, tungsten carbide material is primarily machined used EDM method due to its difficulty and conventional machining. The fourth stage is final machining. CNC machining centers ensure that the dies are brought to desired dimensions specified in the technical drawings. The fifth stage is grinding. Grinding is a process used to remove material from a workpiece with a grinding wheel, creating a smooth surface texture. In cold forming dies, this is a manufacturing method used for parts requiring contact with the workpiece due to very narrow tolerances. The sixth and final stage is polishing. This method is applied to make the die surface bright and decline the friction coefficient. This process is very important factor in die life as it declines the friction coefficient at contact point between the die and the workpiece. In the current situation, the production of M30 bolts was carried out in two separate operations. The image on this slide illustrates the stage before and after the reduction procedure. These two-stage process presented areas for optimizing in terms of both time and cost, due to swelling in the shaft area when attempting a single operation reduction. The two-step process had been maintained until now. To increase efficiency, these two operations required additional steps. The fundamental reason for our a need for improvement stemmed from the existence of two separate operations. Reduction and chamfering operations were performed separately. The speed of this operation, carried out with a hydraulic press which is quite slow, was 15 mm per second. This situation extended the production time and reduced overall efficiency. Our project objective was to simplify the process and reduce the number, time, and cost of operations by preventing swelling in the shaft area. This is the shaft area. The parts numbered 1 and 2 in the slide represent first and second station samples of previously produced workpieces, illustrating what we faced before the improvement. In this section, we will focus on our design and simulation. The results of trials conducted before reaching the optimum chamfering angle are presented. The sectional view of the die created for analysis for swelling values of dies with different chamfering angles are outside the customer's expected range. The customer expected a swelling of less than 0.1 mm. Specifically, the swelling values observed in the given chamfering angle dies highlighted the necessity for design optimization. These simulations allowed us to reduce the number of physical trials, thereby saving both time and cost. As a result of analysis, a 15-degree chamfering angle was determined to be optimum angle. In this slide, you can see the swelling values in the workpiece cross-section achieved with this optimum design. As observed, this design reduced the swelling in the shaft area to acceptable levels, improving product quality and eliminating the need for subsequent operations. This significantly improved our ability to perform a combined operation in one single die. The animation of the completed 2D simulation is also shown in this figure. Now, let's turn the tangible outcomes of our study. This table clearly summarizes the improvements we achieved. Number of processes. We changed from two separate operations to one combined operation in a single die. This significantly simplified our production process. Production time for one bolt reduced from 45 seconds to 20 seconds. This represents a reduction of over 50%. Annual production time for 50,000 units. It is decreased from 625 hours to 347 hours. This shows an annual saving of 277 hours. For about cost, we achieved a reduction up to 50%. Energy and resource consumption. We observed a reduction of up to 50% in both energy and resource consumption. An order status, this customer transferred new orders to norm tooling. These results clearly demonstrate the positive impact of spatial die design and cold forming optimization on the production processes. Thank you for your attention. This study is a great example how engineering approaches and R&D activities can improve industrial productivity. Now I'm open to any questions you may have.
Hande Hanım, sunumunuz için teşekkürler. Thanks for the presentation. Herhangi bir sorumuz var ise yaklaşık bir 5 dakikalık süremiz var. Soruları alabiliriz. If you have any questions regarding the presentation or its constituents, we have enough time for this.
Can you hear me?
Yes, we can. If you have
Okay.
questions.
Thank you for this very nice presentation. I was just curious about the simulation, like which software or program did you use for the simulation?
Hande Hanım,
Oh, sorry. I have just turned off my microphone. It was simplified forming.
Simplified forming. Okay, thank you. Thank you very much.
You're welcome.
thank you for the question.
Benim bir sorum olacaktı.
Buyurun.
I have a question. Thanks for the nice presentation, Hande. I have two questions actually. First one, how cold forming increased the mechanical behavior of materials? I mean, what changed inside of the materials?
Okay. Before heating, with heating, it changed surface quality and material properties. Cold forming keeps a material same each area. So also it affects its surface. It is very well behaved when we compare with hot forming.
Okay, thanks.
Well,
Okay,
yeah.
please continue, yes.
That we can discuss about this, like how can we say it is used cold forming instead of hot forming to get a better quality bolts, and cold forming is much more expensive than hot forming, by the way, because their dyes are quite expensive than hot forming, but still we need cold forming instead of hot forming because of the mechanical properties.
Oh, thanks. And the second question is, did you make any experiment result? Did you make any experiment to support your simulation?
Well, we have just produced that dye and we send it to customer and they tried and they
They will send you result.
enough.
Yes.
It was a customer request actually first, because they said, is it possible to make this dye in one dye, because we use two dye for this section, but if you may, they know that we have opportunities to simulations, so they offered us, can you make this dye in one? So sorry, I explained very
No, it's okay.
sorry
It's okay,
for
don't
my
worry.
explanation,
No, it's
but
okay, don't worry.
it was a customer request.
And there's no complaint about, I guess it was confirmed by your customer.
Sorry, I couldn't understand this. Sorry.
I guess there's no complaint, or your customer was so satisfied, so that's the confirmation of your study, I guess.
Yeah, they were very happy, and they visit us during the production, and they asked us, is it really possible? Like, they couldn't believe that we made this actually, because they are doing this for a very long time in two dyes. Now we send it in one dye, so it's very also good for them for cost.
Okay.
Okay, thanks. Thank you, Hande.
Thank you. So we are in the last 1 minute, so I guess we are over for the questions. So we are going to continue with the third presentation, which is going to be presented by Mokrani, Elhachmi, and the team. So the title of the presentation is The Influence of Zinc Acetate, Zinc Chloride, and Zinc Sulfate Precursors on the structural, morphological, and optical characteristics of zinc oxide thin films deposited via the SILAR technique. I guess I made it in a proper way. Sorry for the chemical formula.
Hello, everyone.
Can you share your screen or?
Yes. I'm Noor Huda Mokrani, PhD student at University Mohammed Khaydar Biska in Algeria. I would like to thank everyone here for attending my presentation. Influences of zinc acetate, zinc chloride, and zinc sulfate precursor on the structural, morphological, and optical characteristics of the nanoparticle field deposited via the SILAR technique.
Miss Mokrani, is that possible for you to share your screen? Because we cannot see it now. Maybe you can try it again.
Yes. You see?
I can't see. I'm going to ask the other participants if they can see, if anyone can see.
I cannot see.
No, we cannot see.
Maybe you can try to share full screen, not the window.
Yes.
Yeah,
Yes.
here we are.
Thanks. Excuse me. The plan of the presentation, introduction, results and discussions, and conclusion. The development of thin films has major key challenges such as extended production periods, economical materials synthesized, and silicon-based machine technology, which has pushed this technique to the high cost. However, various thin films fabricated techniques such as spin coating, sol gel, spray pyrolysis, electro deposition, chemical bath deposition, manitron sputtering, and SILAR. SILAR provided appealing advantage over other deposition process such as simplicity, reproducibility, environmental friendliness, cost effectiveness. Materials and methods. The nano films were grown on glass substrates via solution-based SILAR route at room temperature and atmospheric pressure. The shell of the synthesis of the ZNO pure and thin films for on one SILAR set is shown in figure 1. Results and discussion, characterization of thin films, XRD, SEM, and DX, visible. Figure 2 shows the XRD patterns of pure nano films. We observe three strong reflecting 100, 002, and 101, which correspond to the hexagonal one-side structure. This result is consistent with previous studies. The intensity of the diffraction peaks decreases by zinc sulfate. The presence of sharp and numerous diffraction peaks indicates that the polycrystalline nature of the films. The EDX,
Miss Mokrani,
yes.
I'm so sorry, Miss Mokrani, I'm going to interrupt you. Can you try to click on the page that you are now describing, because we still see the first page of the presentation. Maybe you can click on the page which is on the left part. Yeah, and by each time you can click on the page so that we can follow.
Yes. You see?
Yes, we can see now. You can continue.
Yes.
Thank you.
Thanks. Figure 3 demonstrates that the synthesized ZNO samples comprised just Zn oxygen and silicium elements with no other elements of contaminant discovered in any of the purity of the thin films. It has been observed that the surface shape changes with changes in zinc precursor. Pure ZNO consists of mixed grain-like particles in the case of zinc oxide from an acetate source. The grains in the sample become larger than the grains in other samples. Moreover, the pores on the surface of the sample become larger than in the pores of the other samples. As for zinc oxide from sulfate source, we notice clear differences where the particles are like flowers. Figure 5 shows a plot of the optical transmittance spectra of the film as a function of the concentration in the wavelength range from 2000 to 200 to 1200 nanometers. The optical transmission value of ZNO film from sulfate sources is higher than that of other coated films. In the present work, the structural parameters, microstructure, morphology, and optical properties of pure ZNO at different precursors of thin films. The studies indicate that all ZNO films deposited by the employed SILAR methodology exhibit promising structural. The ex-ante data shows a polycrystalline for all the samples. The same pictures suggested that the conversion of nano-flower-like morphology into flower-like nano-needles interconnected with the topology zinc sulfate. From these results, we conclude that the new film shares their structure with the Shenzhen precursor. The references of the introduction, and thank you for your attention.
Thank you for your
Thank you.
study and the presentation. Do we have any questions for the presentation? Miss Mokrani, can we turn back to your presentation, because we still have time? And is that possible? Is that possible for you to reshare your screen?
No. Yes.
Sorusu olan arkadaşlarım varsa alabiliriz. Okay, I'm going to ask only one question. I'm not familiar with the study but I just wondered, okay, producing these zinc oxide thin films, do you want this flower-shaped appearance in the SEM appearance tool, or it is not desired? I just wondered if this is in the conclusion part. You mentioned about this flower and non-flower appearance. So which one do you want from this film? to have. Mokrani, can you hear us? Okay. Thank you for the presentation. Now we are going to continue with the next study. She's going to be presented by Nadjette, Belhamra, Sabah, Haffas, and Norel Hoda Redhosh. The title of the study is The Impact of SN Doping on Physical Properties of Cobalt Oxides, I guess, Nanoparticles.
Hello, everyone.
Can you share your screen?
Yes.
Oh. Okay. Thank you.
Hello, everyone. I am Haffas Sabah. I am a PhD, University Biskra, Algeria. My presentation is the impact of SN doping on physical property of CO3O4 nanoparticle. Presentation plan, introduction, deposition of cobalt oxide thin films, result and discussion, and conclusion. Introduction. Cobalt oxide, especially CO3O4, is one of the most studied transition metal oxide due to its importance for various scientific fields. It is used as catalyst, field emission materials, absorbing layers in photovoltaic cell, and magnetic material. CO3O4 oxide is a p-type semiconductor. It crystallizes in a cubic spinel structure. This is a figure of CO3O4.
Ms. Sabah, can you click on the slide or the page you are describing so that we can see as well? Thank you. You can continue in that way.
Yes.
Thank you.
Deposition of thin film CO3O4 is we use synthesis via the co-precipitation method. We dissolving cobalt chloride in distilled water, followed by the gradual addition of a basic solution such as NaOH and their continuous magnetic string at 60 degree. And then dried and calcinate at 500 degree to convert into crystalline CO3O4 with a spinel structure. Research uses the co-precipitation technique to prepare pure cobalt oxide nanopowder and 10 doped CO3O4 with different percentage of tan from 2 from 2 to 10 of white. It also studies the leafy of tan doping on the structural and optical properties of the CO3-O4 nanopowders.
125.000 TL ama tam bizlik anne. Kira mı satılık?
Result and discussion. Result. We can listen.
Yes, we can hear you. You can continue.
Result and discussion. The structural properties we used analysis of DRX. The figure is show the DRX pattern of CO3-O4 doped of SN. We see the result confirm the formation of a cubic spinel structure CO3-O4 by the characteristic diffraction P corresponding to the 11, 220, 222, and 400, 422, 440, and 620 and 551 plants. We see the doping cobalt oxide with 10 in additional peak corresponding to the 311 plant appeared without altering the crystalline structure of the nanoparticles, indicating the 6-fold encrompation of the dopant. The results are simulated in the table. This table. We can see in a table the crystal size is increasing with the increased doping of tan from 44 in 62. And the other hand, the microspan is decreasing of increasing the doping. Which can be attributed to the substitution of CO plus 2 ion by larger CSN plus 2 ion within the CO3 for the lattice. As a main analysis, the morphology of CO3-O4 nanoparticle was studied using SAM. It was found that these particles are very small sphere clustered in irregular clusters due to their small size and high surface energy. This indicates that the studied samples are nanoparticles of the same size as these clusters. Clustering is due to the effect of the aqueous suspension, which results in the formation of the Parker agglomerating structure. After analysis, we can see in this figure two weak absorption bond were recorded at 690 centimeters and 596, confirming the spinal structure of CO3-O4. The observation bond at 690 corresponding to the stretching vibration of CO plus 2 to oxygen, while the one at 596 is attributed to the CO plus 3 to oxygen vibration. Upon the point CO3-O4 of with 10, a slight shift in the with number value was observed, indicating successful encroachment of the dopant, confirming that the material has crystallized with the nanoscale ring. Conclusion: In this work, we prepare nanopowder of pure cobalt oxide doped with 10 in different percentage from 2 to 10 of white. The powder were prepared using the co₃ method with the work aimed to study the effect of doping on the physical property. X-ray diffraction study show that the 10 doped cobalt oxide powder has a cubic crystal structure of the spinel chip. The grain size of the prepared nano oxide play an effective role as the larger the grain size, the lower of the distortion value. In addition, the infrared study show recording of transfer stretching vibration of the hexyl group in the functional region and under observation due to the Cl bond in the fingerprint region. Scanning electron microscope analysis provide that the prepared material is in the from the element of the small nano size grain. And thank you for your attention.
Thank you for your presentation. Do we have any questions regarding the topic? We have 9 minutes ahead. Okay, if not, in a few minutes, I'm going to continue with the next study presentation, which is the 5th one. Okay. So, Belhamra, Belhamra, you're here?
Yes, I'm here.
Okay, thank you. You're welcome. So we are going to continue with the study named The Effect of AI or A1 Doping on Structural, Optical and Photocatalytic Activity of Zinc Oxide Tin Film Derived by Sol-Gel Deep Coating Technique. So Ms. Belhamra is going to represent the study results and the details. So if you are ready, you can share your screen and you can start whenever you want, whenever you are ready.
A minute, please.
Sure, you have time.
HNO3, chlorine, Belhamra, if it is possible, can you open your camera? Since I am not a chemist, I cannot read.
My colleague from the Congress requires Ms. Belhamra to turn on the camera.
من بعدها كيفاش ندير؟ احتاجي
Miss Belhamra, is that possible for you to turn on the camera so that we can?
Yes. My name is, I'm listening. You are listening?
Yes, we are listening to you.
Okay.
Before you start your presentation.
Okay.
Yeah.
My name is Farial Belhamra. I am a PhD student in Algeria. My work is effects of AL doping on structural, optical, and photocatalytic activity of zinc oxide in films derived by sol-gel deep coating technique.
Thank you. I'm going to interrupt you for all of us. If possible, please, all the participants, if it is possible, can you please turn on your camera?
Okay. Okay. Presentation plan, introduction, experimental détaillé, result and discussion and conclusion. Introduction. Zinc oxide thin films is semiconductor well known for its structural, optical, and electrical properties. Is valuable in optoelectronic, gas sensor, and photocatalytic application, particularly for environmental and energy solution. However, pure zinc oxide face challenge like rapid charge care, recombination, and limited light absorption, recombining enhancement to improve its efficiency. Aluminum doping has proven efficiency in modifying zinc oxide properties by turning the band gap and reducing localized state, change the morphology of zinc oxide and enhancing electrical conductivity. This modification significantly improves zinc oxide photocatalytic performance and broaden its particle application. This paper examines the impact of aluminum doping on zinc oxide, focusing on the relationship between structural, optical, and electrical change and their role in optimizing photocatalytic efficiency. This my expérimental détaillé. La source de materials, zinc acetate déhydraté and aluminum nitrate nanodehydrate and propanol 1, monoethanolamine, solution A and 2, and my technique is the deep coating technique. Characterization technique, X-ray diffractometer, la microscopie électron abalayage, and 4-point proper. Result and discussion, structural properties. This figure represents the X-ray diffraction pattern of the prepared and doped and aluminum doped zinc oxide thin films at various all concentration. We can clearly see that all doped ZNO thin films have three observed plane 100, 002, and 101, which correspond to the hexagonal word size structure, which PC3MC space group, according to the 003 145 card. It has a peripheral orientation along to 002 direction. It was observed that the peak 100 and 101 intensity increase as the aluminum oxidation increased. Now, a related phase of aluminum was observed in the X-ray diffraction. It is concluded that aluminum ions are successfully formed at the lattice site. This figure represents the variation of the crystalline size and strain various aluminum concentration. This figure described how aluminum doping effects of crystalline size and strain in zinc oxide thin films, initially increasing aluminum concentration up to 3%, reduce the crystalline size from 35 nanometer to 27 nanometer due to the lattice constriction caused by the smaller aluminum ion releasing zinc Zn to plus beyond 3%. The crystalline size increase again, likely due to the aluminum accompanying international seats. Expanding the unit cells strain show the opposite behavior. It increased up to the 3%. Due to the lattice destruction, then decrease as the structural stability. This indicates a non-linear anisotropic structural represent aluminum doping. This figure represents the morphological properties. The SOM analysis of zinc oxide thin films doped with varying concentration 0 to 5% reveal a strong correlation between surface morphology and crystalline size. And doped zinc oxide show large agglomerant and minimal strain, indicating will crystallide grain. As aluminum doping increased to 3%, crystallide size decrease and strain increase, indicate lattice distribution from dopant intervention to 4%. Partial recovery in crystallinity is observed. At 5%, the film exhibits renewed agglomeration and vinylation morphology, likely due to the phase expression of crystalline from existing doping. These trends are supported by literature. This figure represents la photocatalytic degradation analysis of methylene blue. The photocatalytic activity of undoped and aluminum-doped zinc oxide thin films was assessed throughout sunlight-induced degradation of methylene blue. The degradation rate with turbation rate and absorbance change at CC0 nanometer result, and figure 2 how that both undoped and aluminum-doped thin films efficiency degradate methylene blue, confirming their photocatalytic efficiency as shown in that figure. Photocatalytic efficiency variant with aluminum doping. Undoped zinc oxide achieved the height degradation 1991 in 4 hours, efficiency declining with height count dropping to 79%. Optimal doping level like introduction defined a recombination syndrome that reduce activity. This finding contrasts with the reported this corresponding possibility due to the different sentences or the testing condition. Conclusion. It can be concluded that the zinc oxide thin films are successfully doped with aluminum atom by varying the molar concentration of this atom using the deep coating sol gel method. The X-ray diffraction pattern confirmed that the film have a polycrystalline nature with hexagonal world size phase, and the peripheral orientation peak are 100, 002, and 101. The crystallinity decrease from 35 nanometer for the undoped zinc oxide to 27 nanometer for the doped with 3%, and increase therefore SOM image revealed that the film having a uniform surface devoid of imperfection and crash-free increased aluminum doping in zinc oxide thin films reduce optical transmittance in the visible and near region while maintaining strong UV absorption. The optical band gap variation between 3.31 and 3.11 electron volt, enhancing the concentration of aluminum doping. First, increase shape resistance reached and examined for 1%. Then increase where conductivity exhibiting an positive behavior, hitting low values for 1%, and raising as the donor level improve. The photocatalytic application of the film is investigated the monitoring methylene degradation and solar irradiation. We observe that the degradation rate is decreased at high doping concentration. The pure zinc oxide and aluminum dope zinc oxide 3%. Present the best catalytic performance with blood methylene degradation up to the 99%, degrading just 4 hours of irradiation under solar light. Thanks.
Thank you for your presentation, Ms. Belhamra.
You're welcome.
Thank you. Do we have any questions regarding the study? There is one question from Merve, I guess, but
Actually, I wondered, did you check your catalyst stability after your tests?
Ms. Belhamra, did you hear the question? Could you hear the question? Ms. Belhamra, are you online? Are you with us?
I'm here. The connection is not correct.
Okay. Can you hear us now?
Yes.
Okay. Maybe we can repeat the question.
I just wondered, did you check your catalyst stability after your test?
Application photocatalytic.
Yeah.
Yes. What is the question?
Did you check your catalyst stability after your test? Did you try same catalysts after for second time, I mean?
Second time?
Yes.
I am not understand this question.
After you complete photodegradation test, did you get catalyst?
Yes.
Then did you try again same test with same catalyst? Did it stable, or after one test it composed, decomposed?
I think they didn't do any further study. Okay, if Miss Belhamra will not going to continue, will not going to answer, we can continue.
I am not understand.
Okay, I guess the question was about the catalyst that you obtained. I'm going to thank you, Miss Merve, for your question, and thank you, Miss Belhamra, for your study presentation.
You're welcome.
So we are going to continue with the sixth presentation. We are 4 minutes. Okay, we have 4 minutes more. So if we have any more question, we can.
I have a question. Belhamra, there was a graph about the relationship between the crystal size and strain in your presentation. And the graph showed that when the crystal size increase, and also strain decreases. What is the main reason of that behavior?
Thank you for the question. Do we have any answer, Ms. Belhamra, for this question?
Repeat, please.
There was a graph on your presentation. It showed relationship
For
between
crystal size and strain?
Yes, grain size and strain. When grain size decreases, strain increases. What is the reason of this behavior?
Initially, increase the aluminum concentration up to the 3%, reduce the crystalline size from 35 nano to 27 due to the lattice contribution caused by the smaller ion aluminum replacing the Zn this ion. This is?
I try to get it.
Okay.
Thank
If
you.
this is enough
Thank
for
you.
you.
I
Thank
think
you for the question
it's
and the
okay.
answer.
Thanks.
Okay. Thank you, Mr. Yalçın, for your question. So now we are going to continue with the study titled Mobility Modeling in Diamonds, Accounting for Intervally Repopulation in Charge Carrier Transport. İshak Deniz, Co₃ and Weingarten are the authors or the researchers for the study. So I think who's going to?
Yeah, thank you very much. So can you hear me?
Yes, we can hear you. We can see you as well. So I will ask for you to share your screen if possible.
Okay. Can you see my screen?
I can see it. I think my colleagues, the other participants also see as well.
Yes, we can see.
Okay.
Okay, thank you.
You can start if you want.
Thank you. So my talk is about mobility modeling in diamond. And I wanted to talk about intervally repopulation effect, but unfortunately I didn't get my desired results. So maybe, okay, not much about that, but still about mobility modeling, because we have many models. And I'm a PhD student in Dukuz İlül University in Izmir, but I'm doing my work in Technical University of Dortmund in Germany. And my work is supported by the Alexander von Humboldt Foundation. Okay, so first, like a little bit advertisement for diamond, like why? Because in the detector technology and in the electronics, the silicon is the dominant material. But still, diamond have some potential applications in near future. And it's because of its radiation hardness and its temperature resistance and chemical inertness, its large band gap, high charge carrier mobilities and saturation velocities. Because of these properties, it's a good candidate as a sensor material in high rate, high temperature, and high radiation environments. So currently it's also used, but like in future we expect its large scale application in high energy physics, in nuclear engineering, fusion energy, in space application, and in dark matter detection. Also, its near tissue equivalence in terms of atomic number and energy absorption makes it a sensor material in radiation therapies. And in electronics, from electronics point of view, it's an emerging semiconductor substrate for power electronics and radio frequency applications. It's environment friendly, consistent with the REACH policy of Europe. And you can see here in this web diagram that its properties outperforms all other materials in band gap, in thermal conductivity, and critical electric field, and all properties. Okay. So why do we need diamond detectors? Here's a little preview. It's because of its, if we compare it with silicon, it has a band gap, like a very large band gap of 5.5. Output is like low noise. Its atomic number is 6. It's a demerit. But also a merit for tracking detectors. And its displacement energies makes it radiation hard. Its high mobility gives a fast signal. Its saturation velocities are also very high. And here I put as application. Currently, it is used in sun as beam condition monitors. You can see it here in the red circle. There are 3 small spots. These are actually the diamond detectors for monitoring the beam condition of the accelerator. So these are used in sun and also in Fermilab and other high energy physics experiments around the world. But it's only one application. There are, of course, other applications in the nuclear physics, like in the nuclear reactors and the fusion reactors, and everywhere, like in the space. Okay, so what is detector physics? It's a little bit like I can describe here, like it's when an incident radiation comes, how can we detect it? It hits the detector material, creates a hole in electrons, which drifts under the applied field towards the electrodes, and then we get the signal. Then we can process the signal, we can amplify and see like what is happening and what kind of particle was it. And so my work is about this propagation part, like charge propagation, charge transport. And the material, the detector material is diamond. I'm looking for like how these electron hole pairs drifts in diamond after it's created by an incident particle. Okay, so a little bit about this transport mechanism in the solid state. So it follows generally the Boltzmann transport equation. I will not go to the detail, but it's a Boltzmann transport equation that it's widely used in many fields of physics, including our part, like in the high energy physics. But in this form, this equation is very complicated. We can reduce it. We can simplify it by assuming some assumptions, which are I listed here, and by taking into account these assumptions, we can reduce the Boltzmann transport equation into this form, which is called the drift diffusion model in semiconductor physics. So in diffusion model, then the most important parameter is the mobility that I'm going to talk about it. And this mobility is theoretically related to the mass and effective mass and the scattering rate of these electron hole pairs that we can see here. So these electron hole pairs, when they drift, they scatters with the different atoms or lattices, phonon lattices, etc. And depending on these scatterings, it determines the effective mass and this also the mobility of the electron hole pairs. So theoretically, mobility is related to the scatterings, but the Matheson rule. But by calculating mobility like in this way, it's very difficult. And solid-state physicists do it in this way, but we, as an experimental physicist in high-energy physics or in detector physics, we don't do like this. We do it experimentally, like in this way. So we have our sensor, we apply an electric field, we then calculate the drift velocity, we plot the drift velocity against electric field, and we calculate the mobility. So, but the problem is like the mobility not a constant this way. Mobility itself is a function of electric field, and it changes when we change the electric field. And this in this way, this equation then transforms into this formula, which we call the Co₃ model. So here we can see that mobility is also the function of increasing electric field, and mobility also changes in this way. But this model was used for silicon, and for diamond, the different detector physicists, they were using different models. One was Treffer-Minkoff, one was this model, and we were a little bit confused, like, okay, which model should we use for this? I started a study. I did like some literature study for the past 20, 30 years, and I saw, I tested this data, I digitized this data and tested for different model. Like I used different models and then compared the models, like which model best fit to this data. And I found like the Co₃ model was a bit better model to describe this data. So here you can see it for the for electrons. We are getting the parameters here, like this beta parameter EC and the low field mobility, EC, beta, and saturation velocity. These three parameters we got. So these were not extracted like in this way before. And also I did it for the holes, and after that, okay. Then there was a thing here, you can see that there are different patterns like this blue lines and the red lines. And when we look at it like why there is difference, why different literature data give different values for the same electric field, and we found it's because of the source. So those who used the laser source in the experiments, they had lower drift velocities, and those who used like alpha particles, they got like a little bit higher velocities. Okay. Then my task was to implement these characteristics in the ALPX² simulation framework. It's modular framework. It's developed on the Monte Carlo based simulation. It's simulation framework. Also, it's used for energy deposition like GN4, and for importing electric field, it imports the electric field from TCAD also. And for data analysis, it depends on root or any different data analysis framework. So my task was like to implement this diamond into this ALPX². And okay, for this I did this kind of simulation you can see here is my diamond, and here is the alpha source. It's shooting the alpha particles to the sensor. Then I calculate the drift time, like drift time from when electron hole pairs are created here, and it moves again to the other towards the other contact. So here you can see when alpha particle comes, it deposits energy in the sensor materials. The hole drifts and towards the one contact, and the electrons drifts to the other contact. And from this, we can calculate the drift time. And here you can see I analyzed the data. I took the drift times for the different voltages, and then I calculated the drift velocities here, and then I plotted it against the electric field. And then I saw like the parameters, if they match with the parameters which are reported in the literature data, and they were. So here you can see I compared this simulation data with the literature data, and it perfectly superimpose on this. It means like, okay, it works, but here we can see a little bit deviation in the high electric field, and it's because of some problems that I wanted to discuss it under this repopulation effect and high electric field, because for this the Co₃ model doesn't work. So here you can see it's only for electrons here, and here you can see it for holes and electrons that we successfully implemented the diamond material and the Co₃ model in that Alpec simulation framework. And we also now want like to do it for this region to describe it. And for this, like we need this intervally repopulation effect things is to take into the account. So in summary, what I did, I implemented the Co₃ model into the Alpec squared simulation framework, which described the mobility values very well in a wide range of electric fields. But at very high electric field, it doesn't work, and a new model needs to be developed for this. We are working on this. So intervalue repopulation effect is observed, and it needs to be implemented here also. A model is under development for this. So next steps for me is to do some TCT experiments that we are doing now, and also to take into, so what I talked about the single crystal CVD diamond, but we need to also implement it for the polycrystalline CV diamond. These characters, we also need to implement it in the simulation framework. Mm-hmm. So thank you for the listening. I'm sorry, I think I did a little bit much then. I took much time.
It's okay. We still have time. We still have 2 to 3 minutes. Thank you for you to share the details of this variable study with us. So
welcome.
Thank you again.
Dr. Faiz, how are you?
Fine, sir. How are you?
Fine. Nice to see you here.
Thank you very much. I wanted to come, but unfortunately, here there were some meetings and I couldn't come in presence. But
next time, inshallah, we hope to see you.
Inshallah, inshallah.
Where are you now? In Germany, in Afghanistan, or where?
I'm in Germany now, in the
Germany.
Technical University of Dortmund. Yeah.
Okay. Technische Universität Dortmund.
Yes. Yeah.
Yes. Very nice. Very nice.
Thank
you for the presentation and participation.
You are welcome, sir. You are welcome. Thank you very much for you to provide us this opportunity to share the work.
It's a pleasure for us.
Thank you, sir.
I would like to thank both of you.
Thank you.
Again.
Thank you.
So if we have any questions regarding the study, I can wait for a few seconds.
We may start the next presentation.
Okay.
Okay.
Thank you.
You are welcome.
So we are going to continue with the next presentation, the next and the last one, with the title Gene Therapy for Inherited Color Vision Deficiencies. It's going to be presented by Ebru Maddem.
Can you please see my screen?
Yes, we can see. You're welcome.
Thank you. So with your permission, I can start if it is okay.
You can start whenever you are ready.
Okay, thank you. Thank you. First of all, thank you for this conference and for accepting my abstract. My name is Ebru Maddem. I'm doing my master's degree at Uskudar University in medical biotechnology. So first of all, just a background regarding the topic. I choose this topic because I have problem with my eyes and I have been going to different hospitals, but I cannot find a perfect solution. So I make a project proposal to my university. I'll be working on this as a research during my thesis, my MSc. So if we look at the context, what to expect during my presentation, introductions, we will discuss what is color vision deficiencies, how normal color vision deficiencies works, and the genetic causes of inherited CVDs, why treatment is needed. And we will also look at the types of color vision deficiencies, and then we will explore the main topic, that is gene therapy as a principle of restoring color vision. We will also look at the type of research that has been ongoing on, that landmark research and clinical trials. We will also look at the challenges faced by these researchers during their research. Then we will do a recap of conclusions and a future outlook to see what the future entails for us. So we have this, I'm just trying to, hold on a second. Just excuse me a second, I'm trying to remove this. Okay, good. You can still see my screen, right?
Yes, we can still see your screen.
Okay, good. Okay, good. So yeah, eliminating the spectrum gene therapy for inherited color vision. So if you look at this image, it depicts a child who is struggling to understand the colors of the rainbows. Now, this is not a gameplay or a fiction. It is the reality that people face, or people who are suffering from color vision blindness. Like, these are the reality that they face on a daily basis. So color vision deficiency is the inability to distinguish certain shades of colors. The term color blindness is also used to describe these visual conditions. So our ability to perceive a rich tapestry of colors relies on personalized cells in the retina. These cells are called conics. Now, as we know, there are three basic types of conic cells. You have the S conic cells. This cell is sensitive to short wavelengths, and that is blue color. So, and then we have the M conic cells, which is sensitive to medium wavelengths, and that is green color. And then we have the L conic cells, which is sensitive to larger or longer wavelength, which is red light. Now, these conics, they also have what we call opsins. These opsins, they are protein pigments. So if these opsins are missing, then that individual suffer from color blindness. So it depends on which opsin is genetically modified. For example, if a person cannot see blue, it means they have problems with their S opsins. So currently there is no cure for color vision deficiencies. There is no standard cure that is internationally recognized, but color filtering glasses offer some assistance. However, these color filtering glasses, they do not address the root cause of the problems. So this left us with an opportunity as well as a challenge for those who are suffering from color vision deficiencies, and an opportunity for those who are interested to research about these topics. It means like we can explore innovative and therapeutic approaches to address this problem. So the types of color vision deficiencies, we have dichromacy. This involves the absence of one of the three basic color mechanisms. One of them is protanopia. It means the absence of red color pigment receptors. I explained before about the cornets. We said that red L was sensitive to red. So if a person is having this type of color blindness, it means they have an absence of L pigments, which is missing in their genetic makeup. And the second one is deuteranopia. It means the absence of green pigments. So this individual lacks M absence, so which makes them to perceive green color and brown color almost the same, or the green color become dark to them when they look at it. And the third one, we have trinotopia. It means the absence of blue. We said that S was responsible for blue, right? So if a person is having a missing pigment, that person have problem in identifying blue colors. So we have anomalous trichromacy. This involves a defect in one of the three quant types where the photopigments has an altered spectral sensitivity. So in this case, the protein which is responsible for sensing light or the specific light is not actually absent, but it is been modified. It means there's an extent or there's a specific percentage to which these persons cannot see clearly whether this color is blue, red, or green. So, and then, yeah, one of them is protonormally reduced visibility or sensitivity to red. Just like as we discussed, red was related to L absence. So these persons has a minimal tendency to mix colors that are red or see a red color as if it is dark. We will get to the percentages. And the chromacy is similarly sensitive to green. The person have problem in distinguishing green colors. And tritomale reduce the sensibility of red. Now, the last one, monochromacy. This is a very rare genetic conditions, and then it involves none or one of the contypes are functionals. Individuals have very limited or no color visions and often experience other visual problems like poor visual acuity or light sensitivity. So this is an image showing how people suffering from different types of this color vision deficiencies will see a picture. So this is a normal trichromacy, and these individuals will see this picture differently, likewise this and that. So this, for example, a person who is suffering from protonormally will have 0.66% of confusions of the specified color. And then, yeah, so like basically these are the percentages. So we discussed about gene therapy as a principle to restore color visions. So we learn in genetic mutation, for example, when it comes to point mutation, you can use a secondary mutation to rectify that initial mutations. So here, similarly, we use something like that. So gene therapy offers a direct approach by targeting the underlying genetic defects responsible for the inherited color vision deficiencies by delivering functional copies of the mutated gene to the affected retinal cells. The goal is to enable the production of the missing or non-functional photopigments. Now, there's what you call viral vectors. So these viral vectors, they are actually modified viruses which are used in this treatment. So in this treatment, the most important factor is precision to avoid off-target, because when there is an off-target of treatment, it can lead to detrimental consequences for that individual. That's why these treatments, up to now, it is not 100% approved by the FDA, or it is not 100% tangible, we can say. And the viruses that you use here is AAVS, adeno-associated viruses, which are used in this treatment currently. So as I mentioned here, precision is really vital, like when it comes to this type of treatment. So early clinical trials. So like one of the most fundamental trial which has been done so far is the liver congenital auromosis caused by mutation in the RPE65 gene. While not directly targeting the red-green deficiencies, these trials have provided valuable insight into the feasibility and potential of retained gene therapy. So I have read articles based on this, and it started since 2009. Because now in this gene therapy, there is limited data, which I have realized. There is limited studies which have been done on this, but new research are coming up. So we look at the landmark and research, landmark research and clinical trials. Early success in achromatopsia, research on achromatopsia, a severe form of CVD involving the absence or dysfunction of all three. Yes?
You have last 20 minutes.
Okay. Thank you for reminding me. So I will just, without going on each point, I will just summarize everything. So yeah, as I was mentioning, so initially they started with the animal models, and animal models have shown great success, especially in the dichromacy. Yeah, so this basically is the design. If you look at the design in the treatment, there is not enough data which is available for experimental trials. So what type of challenges do they face in this treatment, like complexity of the color vision, and also not understanding the genetic makeup of different people, because everyone comes with unique type of problem. So, and since there is no much data available or much assessment has been done, it becomes a very big challenge, as well as ethical consideration. People do not believe in this form of treatment sometimes. Yeah, this is the same thing. I'll pass that. A feature, so like a feature painted with possibilities. This means there is a lot of opportunities for people who want to explore in this domain, and then a lot of discoveries can be made on that. This is my presentation, and these are my references. I thank you for your kind attention.
Thank you for your presentation.
If you have any question.
If anyone has any question.
Ebrima, thank you for the presentation.
You're welcome.
I think it's a very popular topic today.
Yeah, exactly.
Who was your advisor?
Currently, I am in my second semester for my master's degree. So I will, so I will choose the advisor after finishing this semester. But I am working with Muhsin Hoja. He is really good. I may choose him. I have like 3 professors that are on my list. Right now, I'm just checking which of them I should go to.
Yes. So did you prepare this study yourself only?
Yeah, I prepared this by myself, but now I have a project that I should present on Monday on my, like, it is part of our lessons. It is called experimental trials in animals, something like that. So like it's part of our project there. We are 4 people, but they were not interested in doing this presentation or coming to the conference. So if that is approved, then we can move. I can do that in my thesis.
Okay.
Yeah.
Thank you. Where are you from, by the way?
I am originally from the Gambia. Like my mom is Senegalese, but my father is British.
The Gambia, Senegal, and Turkish.
Yeah.
Okay.
And Turkish. Yeah. Thank you so much.
Okay. Nice to meet you.
Nice
Thank
to
you
meet
for
you
the
as well.
presentation.
Okay. Thank you so much. Stop my.
Bilge hocam, bütün sunumlar tamamlandı mı?
Tamamlandı hocam. Eksiğimiz yok. Zamanlamamız da uygun.
Hepsi yapıldı değil mi hocam? Ben
Hepsi tamam
arada
hocam.
takip edemiyorum hepsini.
Hepsi tamam hocam.
Tamam.
Sadece son olarak herkesin de kameralarını açıp ekran
Evet.
görüntüsünü almak üzere bir benim bir uyarım olacak. Yapayım mı izninizle yoksa
Tabii
var mı
tabii
sizin
hocam.
belirtmek istediğiniz?
Buyurun hocam.
I would like to thank to all of the participants for their excellent presentations. So I want all of you to turn on your cameras so that we can take a screenshot.
Hocam kameram çalışmıyor ama yapacak bir şey yok herhalde bu noktada.
Tamam, evet.
Evet, yapacak bir şey yok.
Salisu,
Evet hocam başlayabilirsiniz siz.
okay, thank you everybody
Thank you.
for contributions.
Thank you.
Hocam size de teşekkür ederiz. Arkadaşlar katıldığınız için hepinize teşekkür ediyoruz.
Teşekkürler
Çok
hocam.
teşekkür ederim.